Okay, can people hear me all right? It's Mocconi, not macaroni. Although they're both commonly Italian, so it's okay. Okay, and of course, macaroni is also wireless. Okay, so I'm the light entertainment before the coffee break. I'm amused that everyone talks about VMware and Intel, and in Cambridge, what we do is Zen and ARM, and there are more ARM chips in the world than Intel chips. So you should remember that. And we have a 1,000-core ARM processor in our lab working. So you should think about data centers with ARM processors and what the disruptive effect that will have on people's virtualization, because most of the virtualization relies on some very important tweaks in the processors, and ARM are different from Intel in how they do that. Anyway, that's not the topic of my talk. That's just an observation in the last 2 days. I'm going to talk about a sort of personal narrative history of the last 12 years of what I've been doing in Cambridge. So prior to being in Cambridge, I was at University College in London for 22 years, a sort of sabbatical, because before that I was in Cambridge. So I went to London for a short break. I had a family, and then went back to Cambridge. And now I have no life. I'm just doing crazy stuff. I'm going to talk about this thing that doesn't really directly relate to cloud. So it's kind of like Deborah Estrin's talk. But like Deborah's talk, I'll try and bring it back down to earth with a sort of cloud edge towards the end. And part of this is also about research philosophy. So the subtitle here is Ignoring the Fashion in Internet Architecture and Being Deliberately Contrary. Contrary to the sort of what everyone else is doing deliberately. The sort of narrative history goes, I'm going to talk about a project we had starting 10 plus years ago called Haggle, which I'll explain in a bit, which is a software architecture which has influenced people in content-centric networking, which is one of the future internet architectures for delivering large amounts of content, which of course comes from the cloud. I mean, YouTube is a cloud service, if you like. And how do we scale that? I'm going to then say how we got into the declarative data-driven networking, which is a way of programming network services and is what relates to the background to a MapReduce or Hadoop or whatever your favorite tool is. And then I'm going to say how bizarrely this led us into doing social networking, and then I'll try and conclude. Back in 1981, we were, I think, one of the first 3 nodes outside of the US on the internet, and I was working at University College London, doing my master's and PhD there. We were told by our funding agency that the internet was the wrong kind of network and we should stop working on it. And that, of course, just made us think we must be right. And my graduate advisor actually has a letter, he still has the letter from them saying, please stop working on this. He ignored them partly because they didn't fund us, so that was okay. We were actually funded by DARPA in the US, so that was lucky. So this is after Steve Deering's picture of the internet architecture, and as Scott Schenker said, you know, one of the interesting analogies he drew is between the cloud and the internet is this common narrow waste of the hourglass, which is one of the things it does is statistical multiplexing, and that was the thing that we were told was wrong. You mustn't do statistical multiplexing. We must have hard multiplexed circuits, and that's the right way to do networks because that's what telephones do, and they must be right because they're 100 years old. So, you know, 31 years later, the internet's nearly a third the age of telephone, seems to work okay. So maybe we weren't too wrong. And the internet, of course, has put on weight, and there's all this complexity in the middle, and people have added lots and lots of different things, and this is all about control plane. And in cloud, in data centers, you have all the software-defined networks to try and mitigate the complexity of the control plane, bring it into, as Scott said yesterday, absolutely, I agree with him, that by bringing it into first-class computer science, you can make the programming of the control plane something more tractable, something that evolves faster, is more robust, and so on. And that's all very good too. Of course, what then happens is lots of people have a different view, and they think that we should re-architect the internet in lots of different ways so that we get rid of all that complexity. They may be forgetting that a lot of that new complexity in the waste was put there for reasons that users wanted it. They had requirements for performance guarantees, that, you know, there were design errors of some kind in the internet. The fact that anyone can send anytime to anyone means that you get DDoS attacks and so on. So then people put in intrusion detection prevention systems and firewalls and NATs and so on. But, you know, that might be the right solution. And re-architecting the internet might not be a good thing. So, you know, we have all these sort of half-baked things like IPv6 and so on. And one of the things that happened to me was I was involved in the Internet Architecture Board when we were kind of thinking about what the problems were in, I guess, 1996. And then I was about to move to Cambridge, and I thought, this area is so full of too many researchers. I really don't want to be here. It's got to be the wrong thing to do. There's like a lot of sheep pursuing this future internet, and that must be the wrong thing to do. Let's go away from working on all these things which are boring. And I proposed in an Intel research lab we had in Cambridge this project we called Haggle. And this picture is supposed to capture the rich world that was emerging, I guess, 12, 14 years ago. We just started to see this incredible diversity of devices in the net. Instead of just having big servers and small clients, which has basically turned into thin clients and big cloud, we also have this huge diversity of devices in vehicles, in appliances all around the world, Internet of Things kind of argument, but also personal devices. And it was clear that these devices were being used in a rather limited way, in a rather bizarre way. Actually using Edge to access an internet service, you realize that latency is a killer, and thin client is a really stupid idea. And you've got a device in your hand which has got a gigahertz processor, and it's got gigabytes of storage, and you're not using them. You've got this service out there in the cloud. And you're also accessing over a relatively long-haul wireless link. You're going all the way to a cell tower or a Wi-Fi access point when you could perhaps be trying to communicate with somebody right next to you. And why are you going via this triangulation? What a crazy idea. In fact, mobile users back then had a very poor experience. A lot of the time, applications would not work. And in fact, we have this experience today. Actually, yesterday at lunchtime when I arrived here, the Wi-Fi here was not great. It kept going away, right? And I tried this with 3 different devices, and there was something wrong there. We're not exactly in a low population density place. So people tried to mitigate the problem with the bad user experience of wireless networks by building multi-hop wireless networks, mesh ad hoc networks, all kinds of things. And in fact, you had this whole bunch of work on ad hoc networks. And if anyone's interested, there's a glorious literature of appallingly bad science done on mobile ad hoc networking. There's a great paper, and I can't remember the author, called The Incredibles, which is an analysis of why on the order of 100 papers have incorrect simulation results. But it's worse than that. Multi-hop ad hoc networks were a completely crazy idea when you don't take account of the fact that there's a heavy tail distribution of the density of devices, which means that whatever you choose for your radio strength, your battery life, and your radio type, there are going to be people who are, from time to time, unreachable. And in fact, a significant fraction of people. That's just the nature of a multi-hop radio network. We fix this problem in fixed networks by we throw fibers to villages. We're doing that finally in the UK at the moment, finally putting in fiber out to the rural areas. And then, that gets rid of it. But if you do this wireless, there are going to be areas where you don't get coverage. But you might be sitting next to somebody in a car, on a train, and on a plane. And why are you trying to go over a long-haul wireless link to communicate with them? Of course, there was also a lot of work where academics said, oh, ad hoc networks, I know, we can get Wi-Fi. We'll use Wi-Fi as the radio link protocol. And this is also stupid, using a contention protocol from a mesh network and going multiple hops. It's obvious that your maximum capacity is going to fall off. If you get the best 18% in each hop, then you're going to get the product of that, which is going to go to 0 in a few hops pretty fast if you've got any serious traffic. Of course, military ad hoc networks are different. They don't make these mistakes, and they do better power management. They use different link and MAC protocols. Anyway, there are a lot of underlying problems. We noticed that there are also application layer problems. If you are to confront this situation properly, you need to think about frequent disconnection and frequent degradation of the capacity. That's the world. And it's not the world we sit in when we plug our desktop in or our laptop into fixed internet, although it is occasionally, as was mentioned yesterday by several speakers, systems fail, but all the systems that are working should be able to go and recover in some way. And we should make that transparent, so we should have an application architecture that's not hardwired to everything being on all the time. And the whole system of the internet is now in the cloud. It's architected around a whole bunch of services being always on and always there. So applications survive by using various layers of directory services, like address books mapped to email addresses, Google Maps, search keys to URLs, And in fact, then, of course, the DNS maps names to dynamically choosing via load balancers what actual IP that you go to. And that means you have infrastructure. So we were kind of looking at this and we were going, well, okay, in this world, we could imagine as a physicist, I would go, well, there's these different types of networks. There's a network that's solid, like the internet when everything's working. There's a network that's liquid, like a mobile ad hoc network, where there's a continual changing paths, but there's connectivity, but it's just weak. And then let's get real, there's a sort of gaseous form of networking where particles are bumping into each other and they're moving off somewhere else and losing connectivity. So in this gaseous world, we noticed, in fact, there's a talk right after the coffee break, so I will not use too much time, that Matthias Grossglauser and David Tse from Berkeley had noticed that you can take advantage of these gaseous forms of networks with these encounters and then moving away from radio interference range of one person and getting nearer to another, and you can get a capacity scaling that's actually rather good. And so people looked at us and said, why are you thinking about a network that deals with lots of only occasional encounters, and then how are you going to do multi-hop networking with that world when you're going to have delays? And we said, well, we may have delays, but we may have better capacity than an ad hoc network. There's a result that says this. And so the Haggle architecture would work in this worst case scenario in terms of delay. We'll see how that works in a bit, but actually would get pretty good capacity for some kinds of applications. This might be a rather good thing. And of course, if you do have connectivity, then it just works better. And your applications have been rewritten to this architecture. So the idea is to confront this decentralization and disconnectivity in the whole network architecture. When I put this to Intel Research, the director of Intel Research at the time said, that's a really stupid idea, so you mustn't do it, and so we did it. So that proved, that was a good thing to do. Actually, we still haven't proved right. When I was involved in Internet Multicast in 1987, 88, people said, that's a stupid idea. And then Sprint wrote a report that said, that's a really bad idea. And now, Telefonica and AT&T have IPTV services that are based on that idea. So, it took 20 years. So I'm not holding my breath. It could take another 10 years for this stuff to take off. There are other aspects of what we did, but let me explain where Haggle comes from. Haggle comes from the idea that as devices move around the world, they can build a map of the world dynamically. And you can think of this a little bit like link state routing protocols like distance vector routing protocols. When I meet somebody, I exchange what I have with them. They take that information, meet the next person, exchange what they have with them, and we could epidemically flood this information. That information could contain anything. It could contain my devices' email addresses, the email addresses of people that I've met, the MAC addresses of those people, so that if I meet them in a physical space, I don't have to go via routers. If I don't have routing, it could contain web pages, and I just give web pages to people, and then they could run over the data they accumulate. Every single node in the world could run PageRank on all of that data and build a map of what's the best information at any layer. No layers. We got rid of layers. That's just any information. We don't care what the information is. So Haggle was Ad Hoc Google. That's where the name comes from. It comes from my friend Christoph Dio couldn't pronounce ad hoc. He said haddock. And I went, we'll call it Haggle, like Google. Anyway, and the notion is that every node in the world is running Google on everything as it encounters now. Of course, you'll say privacy, you'll say scaling, whatever. We'll get to that right at the end. So the current software architecture of the network doesn't help you with this model of the world where it's extremely peer-to-peer, extremely every node is a peer with every other node. The original internet architecture was peer-to-peer. Devices were not cut into clients, routers, and servers. Every device could be a server or a router or a client. It didn't matter. But that's all been broken by people, and everything's become asymmetric and divided up. So, and this layered architecture of software doesn't help with that. You have isolation between a file system and the network. So if I want to implement a very simple idea, which is that I'm running a browser, I'm downloading software, I've got it in my browser cache. Oh, look, there's a neighbor of mine over an ad hoc network, and I want to share the cached information. What do? I have to do something special, right? Now, if I'm a web server, I might be caching, and that's okay. But why do we make that distinction? How bizarre. Why do we insist on using the identifiers only of a given layer in that layer? Why do you use any identifier? What does it matter? As long as the identifier is true in some sense, if you can do the authentication. So, I don't care whether I have a layer 2 or a layer 3 or a layer 4 or a layer 15 identifier for something to do delivery. And I shouldn't really care what protocols I use. I mean, if the protocols have similar semantics, that's fine, right? And there's performance aspects, so I should be able to pick those at random, or appropriately. And there's a bunch of great work on that kind of thing in, I think it's Yale, actually. Okay, so here's a Haggle software architecture, which basically is a collection of agents that do various things like resource management, delivery, protocols, that just fit together any old how. And essentially, a device you carry, or a device on a desktop, or a device in a data center, is symmetric in all regards. It can input information, it can output information, it can store information. That information, subject to all your access control rules, which are orthogonal, could be just a cache that other people get at. Okay? So you can see where that's heading. It kind of really does sound a little bit, but this was before, I think, Van Jacobson came up with content-centric networking, and we didn't think it was that at the time. When he said content-centric networking, we went, oh yeah, that is very like what we're doing here. And I think, again, Scott Schenker with some people in Helsinki actually cited what we were doing, and they said, oh, that does look very like content-centric networking. So it's also, of course, necessary that you have an asynchronous programming model of the world. If you're into programming networks, this has to be asynchronous because you have to decouple network failures from application stalling and so on. So everything has to be written to be, message passing asynchronous. That's a given, and then your whole models of reliability completely change in all your protocol layers. How you fetch information completely changes. You get blobs of information from different places. You have to put them together. You might do some clever network coding. You might do that at any layer. We don't really care. We're agnostic about all that. In this software architecture, we have a whole bunch of different types of data. They're all in some classical object-oriented hierarchy. So we have things called data objects, or DOs. This is another joke about my friend Christophe Dio. He never noticed that his name is D-I-O-T, but in French it's pronounced Dio. And anyway, so, and these are basically, you can have directed acyclic graphs of objects. So you can fetch an object by fetching chunks of the graph from different people. But the data object can have sub-objects. The data object filters, and filters can be declared by people or sent to people. They can be local, remote, one-off, or persistent. And that gives you local one-off is a search filter. A remote is a web search filter. So you say to people, I'm looking for data, and that's saying, have you got it on your device when you encounter somebody? Have you got that data? And it might say, no, but I know who has. You might be essentially subscribed to things, and then you're just going to be receiving things other people tell you. Say, oh, look, you're subscribed. And you might just be listening, and you might wildcard these in some way, and so on. So we have a layerless naming system, and there are name objects, and we don't care about, the names have types, so you can match correctly, but we don't care which they are. They just have some associated name to object mapping. I'll go quite quickly through this. And then we have forwarding objects, because this is a system where every device could be forwarding or storing. So we've essentially got it's a store and forward mechanism, but it's a store, carry, and forward mechanism, or ferrying, as some other people have called this. It's a form of delay tolerant networking, which is what the interplanetary networking people term this, and they have a whole architecture, which is also quite similar, sort of parallel evolution of similar ideas here. And then we have sort of connectivities and protocols. And all these things can be exchanged. So you don't think about software update. You meet somebody and they've got better forwarding algorithms. You go, oh, I've got better forwarding algorithms now. Okay, in this system, you imagine 5,000 million, 6,000 million, 10,000 million people in the world with devices all meeting each other and exchanging all the information and gradually doing a Google, and they have all of Google's storage. That doesn't scale. It also has immense problems for security and privacy, clearly, is top of that list. And when we initially did this architecture, we didn't think at all about this. Later on, and I won't say much about this, we had a social networking European project with some people at Eurocom, and they actually did a fantastic job of the whole security architecture for this, and they've now spun out a company that does a secure distributed version of Facebook called SafeBook, and it's better than all the others, I promise. You can get the source code, so it must be. That's my view with Zen. That's why it's better than all the others. You can get the source code. Oh yeah, somebody said they didn't see Zen in the enterprise. That's funny. Morgan Stanley use it, and Tesco, which is the third biggest retailer in the world, use it for their entire back ends. So there's a couple of minor enterprises using Zen. Anyway, people will start using SafeBook because it's great because it does privacy. Okay, we didn't think much about security initially, but then we were trying to sell this software, this Haggle software, well, for free, actually. We wanted to run a big experiment, and I went to see the biggest cellular company in the world, Vodafone, because they have a very big service footprint, and we said, would you like this stuff? And they're a pretty clueful company. They said, we love the idea because you're going to offload traffic off our backhaul, which is rubbish, because we don't spend enough money on backhaul because we like the profits we're getting. Haha. They didn't say that, but that's my interpretation. But they said, we can't really run your amateurish university software, because although we know it's very good, it's an early day, it's an alpha, and you will have big problems, and our customers will suffer PII, personal identifying information leakage, by mistake. You might have some security architecture, but it's half-baked. You clearly haven't got that nailed, and your software will crash. And our customers don't like their phones crashing mid-phone call, or that's bad. And we really, really don't like unexplained bills. And if I turn on my phone here, I'm roamed onto some network, and my bill will be $100 a day. This is not a great thing. If I was running Haggle and I was forwarding data for everyone, my bill would go to some crazy, crazy ceiling. Of course, we'll fix that when we get rid of the outrageous roaming charges, but that's an economic, political problem. So then this is what got onto the second topic. The second topic was, okay, this is the, declarative networking was our starting point. And the starting point here was all of our code in Haggle had been written. We'd done 4 generations. We did it in native code on Symbian. We threw that out. We did it in C# on Windows Mobile 5 and 6. That was very painful, but the reason was that was the most common platform out there at the time. Remember, this is before there were iPhones and Android. And Windows Mobile was quite a dominating platform which worked on more than one hardware, right? And then we did it in Java, and that's what it currently is. There's a C++ port. But anyway, that's all horrible. But then we thought, well, let's go and look at how you build applications in this space. And one of the applications is search over all this data. And we'd read about people doing kind of search mechanisms in very small numbers of lines of code, where you express a PageRank in 5 lines of whatever. And we thought that sounds good. And there were these other overlay projects. Later on, we'll get onto the fact that our favorite programming language is OCaml, and we've now rewritten all of Zen in OCaml. That's a different story. So we came up with this D3N, which is data-driven declarative networking. And in our case, it's sort of disruption and disconnection tolerant. And the idea is just use functional languages which are type safe, and that should allow us to do a lot more checking, which means we can release code that doesn't make those problems for Vodafone. We can run model checkers on OCaml code. We talked to Microsoft because we were still on C# at the time, and they said, we have this new language, F#, and it looks really like OCaml. Well, actually, it looks like Haskell, and they have model checking work on that, and that's great because we could say, does it fit some security property that we want? So we don't do that work, but they could, and that would be made possible. Again, this goes back to what Scott Schenker said yesterday. You take first-class computer science results of the last decade and actually start using them instead of suffering all the pains of writing code in rubbish 35-year-old programming languages, which were great for low-level stuff back then, but we shouldn't be doing that anymore. Okay, so everyone knows what declarative and functional programming languages look like, but functions are first-class objects, which means passing code around the net is subject to certain limitations on what we used to get in active networking. You don't want to do primitive recursion. You rule that out because then you get non-termination problems, and we don't do proof of termination. This can be done in some cases, but not enough. Okay, so I'll zip through this. But this is just saying in the extension of the language to make them declarative data networking, we just copy what the guys have done actually at Berkeley. So you add essentially select into the language. So you've got filters expressed in the language. And here's just to show you, if you add map and reduce, then that's a program for doing a decentralized delay tolerant voting function. So this will be a bunch of people in a room want to run a vote, and they're meeting each other, their phones are exchanging information. And that program over the Haggle runtime will collect votes as you meet people. There may be votes got from somebody else, and then it will accumulate and declare a result at the end. And that's just to show you. I'm not going to go through the code, we don't have time, but that is the nice expression of this. Oh, I should credit, part of this idea came from Timothy Roscoe at ETH in Zurich, who was looking, and also Brad Karp from UCL, who are looking at my students' Haggle code, and they're saying, how do you write distributed applications and know how they're going to really work in a delay-tolerant world? And they have both been involved in this P2 work at Berkeley, and they said, you could look at that, and then you get a lot more simplicity in programming these systems. You might ask, what happens about non-termination because you don't finally meet anyone? Good question. Well, that's something you have to deal with in the algorithm, right? If not everyone votes, not everyone votes. That's too bad. Okay, so the third bit that we got into is social networking. Why did we get into social networking? Well, I'll explain why we did. But this was sort of coincident in parallel with doing the declarative data-driven networking. And basically, we wanted to look at forwarding algorithms for these opportunistic networks, these encounter-based networks. So how do you meet somebody, they say, I'm trying to get some data to so-and-so. How do you decide whether you accept it to send or not? And how would you evaluate that? Well, of course, it's going to depend on the pattern of encounters, the statistics, the properties of the network. If you turn it around, if you were doing fast failure recovery for routing in the internet, or you were doing fast failure recovery for map-reduce algorithms in a data center, you need to know about the failure patterns, right? You need that data. It'd be really nice if one of the big data center vendors would give us, or operators would give us failure data. That would be great, because then we could reevaluate new replacements for MapReduce and so on. Anyway, but we were doing this nice, easier case, which is people walking around with smart devices or driving around with smart devices. Indeed, flying in airplanes. We have people walking around with devices who forgot to turn them off and got on a plane, and then we were measuring how many other devices were not turned off on a plane. And the average is 5, by the way. Of course, nowadays, some planes let you leave your device on. And there's nothing wrong with it, really. It just disrupts the cellular network you're flying over. So we said, oh, let's study this empirically. And we got some Intel motes, and we used those to measure encounters and then see what the work patterns were like of people encountering. We did a non-anonymized data set with a bunch of people who worked at Intel, and then embarrassingly found 2 people who appeared to be together 24 hours a day, and then that next week there was a marriage announcement, and we went, okay, we shouldn't have known that. So now we do privacy preserving, because we're very bad and unethical. Okay, this is the device, you don't care. And this is typically what you measure is just the, over an experiment, you've got contacts, and then there's intercontact gap. There's a duration of the contact and the duration of the gap. And then you plot this over all the devices in some groups. So you might have 100 devices in the group, and typically you see a power law for the intercontact delay and the contact duration. So that turns out it's a heavy-tailed distribution. That means that, in fact, this is just a typical pair of devices, but over a whole set of devices, there are some devices that don't meet for a very long time and meet rarely. There's some devices that meet very frequently, and that's what you'd expect, right? They're basically, if you go to a computer science lab, there are people that sit in the basement and never meet anyone, and you go to the arts faculty, and the people are all in the bars and the clubs all the time and meeting all the time, or down the beach. So, and we know what that distribution looks like. So, intuitively, but we were verifying this objectively. And that gradient actually matters because there's a whole bunch of results on percolation over graphs of certain kinds. This is a temporal graph, but the properties kind of remain similar. And the alpha turns out to be less than 1, which turns out to doom us to not be able to do a finite delay delivery, expected mean delivery delay between a given pair of nodes is not finite, which is kind of bad for us. It means our latency is potentially bad. On the other hand, if you're not trying to deliver data between a pair of people, you're trying to disseminate data to some fraction of people, it's fine. Okay? So there's a bunch of results. This was published in Transactions on Mobile Computing, and Augustin Chantreau's now at Columbia did very nice work on the cleverness in this. We looked at different forwarding algorithms, and this is where we have to cite, where we got some ideas for particular schemes, and whether these would result in delivery or not. So I don't have time to go through all of this. But essentially, the consequences of this are that when you have this density distribution where some number of nodes are disconnected, it may be a large number at any given time, not affordably wirelessly connected, but they do encounter because they drive to town some days, or they walk to town, or they walk to the village, or whatever, then you may be able to come up with a variety of schemes that work well for this, and you may not. So this is where we kind of got social, because we were measuring all this stuff, and I already given you some hints that we're measuring things that are social. Imagine you were looking at different forwarding schemes for this store carry forward network, You can imagine a sort of cheap and cheerful thing, which is wait till you finally meet the destination, and you chat to the people. You finally see, I was in California, I saw somebody I hadn't seen for 28 years, and we had to spend a whole day and night talking. And a lot of information had been cached to deliver. You could be the rich end of the spectrum. You could be a banker and you're profligate, and you just flood everything to everyone you meet and expect them to get on with it and deal with it and flood that information to everyone they meet. Or there could be something smart in the middle. So could we look at the data more closely? And what we have is these encounters. What we're doing is measuring the social fabric of the world, the dynamics of the social fabric of the world directly. Again, we're not the first people to do this. There's a whole bunch of reality mining data at MIT that were the first people to do it. I think we were the second people to do this, to realize we were mining the reality of society. So what can you look at? Well, you can look at more subtle things than the encounters pairwise. You could look at the graphs. And now we've already had a talk about why network science is important. And I totally buy that, by the way. We have an entire group in Cambridge, which is across all of our faculties, which meets every month and has seminars on network science. We have day-long meetings, and we have people from all branches of science, and some less scientific and some more. And we have lots of talks with graphs like that and like this. This is measuring a bunch of students in computer science, and we do k-clique analysis. So it's not strict cliques, it's cliques where there's some connectivity above a threshold. And there's an interesting thing about as you change k, you can sort of see that more separation happening here. But it's quite clear there are two cliques. Now, we gave these devices to people without knowing. We then did a clique analysis of the encounters, and then this is for a 1-week duration experiment. Why is there a pair of people that meet between these two groups? Well, they are first and second year undergraduates. That pair of people are the class representatives, and they go to the class rep meeting once a week, and they meet each other there. So we didn't know that. I mean, we knew it in the back of our mind, but that data just showed that, right? So it shows a social effect. That means if you want to spread a disease across undergraduates in computer science, the people have to stay infectious for more than a week. Otherwise, they're very unlikely to get between one year and the other. So if you're an epidemiologist, no, but seriously, that's what epidemiologists do, right? And if you want to spread information, which is a disease, it's an information disease, then that's what your epidemic scheme has to have as a persistence, how long you cache the information for to give to the next group. Here's another amusing thing, which is, I think this was Infocom 2006, and these are data sets with people from EPFL and Lausanne, Paris, University of Paris 6, and Thomson Labs at the time, and in Barcelona, I guess, Telefonica Research. And there's a couple of people here who show up as going between groups, they've got high betweenness centrality, if you like, as a metric for that, and they are probably Christophe Dio and Pablo Rodriguez, with high probability. I can't think of who else they'd be. And they're people who have actually worked across multiple groups and so on. Okay, so you can base a forwarding scheme on this further information, which is that people are not just have some time before they encounter other people, but they have other properties, like they're in a clique or they're in a different clique at some level. They may have higher degree or lower degree. They may have a very large number of people they encounter because they're the postman, or they may be a computer scientist in a sub-basement. Or they may explicitly label themselves as belonging to an institution as part of their declared Haggle information. And you can base schemes that use this heterogeneously, and we have a scheme called Bubble, which uses global community, local community, degree, and so on. And this is just comparing different schemes. I mentioned rich, poor, intermediate, middle class, and comparing delivery probability and cost in terms of number of packets sent over the network in each encounter. Epidemic is very costly. Wait until we meet the person is cheap, but has a very high, potentially infinite delay. The in-between schemes are trade-offs. Right? Using more information gives you good delivery close to epidemic, but without the costs. Okay. Can you do community detection in a decentralized way? I did k-clique analysis, which means I need to have all that data. Can you do that in a decentralized way? Imagine each node encounters another node. It gets the data from that other node's encounters and so on recursively. After a very large amount of time, each node has a map of the whole world if they have storage. They don't realistically have storage, and it takes too long. So can you, in a decentralized way, work out roughly what's going on? And that goes back to these approximate algorithms. And yeah, you can, and you can do quite well. I don't have time to go into, but you can do decentralized community detection. Okay, so I'm nearly done here. So basically, people in Intel, when we started this work, and in the European Commission who funded some of this work, said, what on earth are you doing this for? It's completely crazy. And more recently, some people have looked at what we're doing and said, oh, that's quite useful. For example, the Red Cross. looked at what we're doing, and we put in a research proposal recently to build networks during disasters. During a disaster, particularly if you have an earthquake or tsunami, usually your power goes away, and eventually your cell network's gone. Okay? Actually, when we had bombs in London in 7/7, the cellular network didn't work for anyone for 7 hours, right? That's pretty bad. 10 million people had no access to communications unless they could go to a fixed net internet cafe or whatever. So the infrastructure breaks in these situations. This Haggle system would deliver information. So in that situation, people say, oh, but you'd only reach some of the people for some of the time. Yeah, well, if you're trying to warn people on the beach there's a tsunami coming, reaching some of the people is better than zero. You can also do really cool things with the Red Cross are really interested because you can build a situational map. So it typically takes 72 hours after a disaster for this emergency service to arrive. They can arrive and be presented with a situational map, which means they know where to go and where not to go because people are self-helping in those places. So that's cool. Commercial case. France Telecom Orange said, hey, we could do free digital newspaper distribution on the metro in Paris. Using this, we can't reach everyone with 3G. We reach a few people with 3G. Then when they go on a train, they distribute the thing over a Haggle-style network to everyone else. We can even do location-based click-through and still deliver that. They don't have to have that urgently because it's market research. We get it later. That's fine. No paper, no 3G cost to everyone, better battery life, better performance. And go back to this result. The capacity of the system is way higher without impinging on backhaul. Right? So there's a practical use, which saves money and makes money. So it's a win-win scenario. And we've been trying to get people to realize this for the Olympics, which happen like really soon now in London. We estimate at least 1 million people with smartphones are going to arrive in London. And you add 1 million people who probably buy SIMs so they don't roam. The network will die. It will just not work. I guarantee you. Don't bother going to London during the Olympics, even if you have tickets. But the application that we were thinking, for this was people are going to be video blogging, live blogging their team, their country or whatever. And they're going to be really upset, and why won't they be able to do this? Haggle would be ideal for that because it would socially distribute to the people they're with. It could even be weighted towards, friends because you have the friend information in this system and so on. There are neat things you can do in there. We actually have an online key distribution mechanism on Facebook that can be then used for this offline securing of data, so you can do forwarding anonymously, but actually reach people that you know correctly and authenticate various things. What's to do next? There are all kinds of interesting pieces of problem in this. One problem is how do you forget information in caches? The cache eviction in this system is difficult because all these degree distributions and delay distributions make the predictions really hard. They're not sort of simple things, and content interest is not necessarily Zipfian anymore. Incentives to stay in the system is tricky. We think there are ways that we could involve the providers to build incentive because we're saving them money. So there might be some trade-off mechanisms there. If you are engaged in payment for people forwarding, you need to have a decentralized mint. And that's hard. You might use Bitcoin. If you believe it, if you know about Bitcoin, there are various strong critiques of Bitcoin, and they need fixing, so that would be an interesting thing to look at. And the last bit I want to say is that, so this is just a URL for you to go look at. I mentioned to a few people. But this is just part of a much bigger picture, and it is exactly in line with what Scott Schenker was saying yesterday. We strongly believe we should apply sort of first class principles of computer science to systems that we build. So we moved into rewriting all this Haggle software in OCaml and F#. That means we can then use model checkers, which means we can demonstrate secure properties and correctness properties and so on, isolation properties. We've now redone that on the work we did in Zen. Zen came out of Cambridge and was sold into Citrix, and luckily for some of my colleagues who were founders, they got 25% of $500 million, and I just named it. So I get free beer. That's okay. But I wasn't actually a shareholder. So, and 9 of my students were there, and they got $1 million each, so good for them. And now we're rewriting all of that. Some of them came back to the university, and we're rewriting in the same way. We have a system called Mirage. You can go find it on the net. It's open source. You can get it for nothing. It does type-safe execution. It does extreme specialization, which is very cool. That basically means you don't have an app written on LAMP, Linux, Apache, MySQL, whatever. You have an app written in OCaml, and it talks to a runtime, and it talks to a hypervisor written in OCaml, which has got a TCP stack written in OCaml, it's got SSH, it's got DNS, it's got OpenFlow in OCaml, and the model checks, and if you don't need some piece, it's left out. And that means that a cloud app written in this system is between 10 and 100 times smaller footprint. So people yesterday were talking about 10x speed ups by various tricks. Well, we're ahead of that, actually. We're talking about 100x speed up with no tricks and safer code. So the point about this is a crazy wild tour through stuff we've been doing in Cambridge that I've been involved in, and lots and lots of other people. I have to name loads and loads of people who are now all in lots of different institutions. Some of them were in Intel, some now at Microsoft, some now in all kinds of other places, Technicolor Labs, Toronto University, all over. The point is that I wanted to say from the very beginning is that I was trying to avoid a top-down agenda to say the problem to solve is the future internet and the future cloud. Cloud 2.0 should look like X. The problem we started with was, let's do something completely crazy that people tell us is the wrong thing to do. We'll then go through a sequence of steps, random walk through the world of what that we have to solve. And then we might end up somewhere that, or some places, we might take several steps that are useful for several other communities. I'm not trying to say these will be replacements for VMware, next gen, or whatever it happens to be, or cloud computing, whatever. But by not being, following this pack of people doing the next thing the industry wants, we're doing the next thing the industry says, well, no. Or have you thought about the way that really breaks us, whatever. That, I think, is the right way for long-term research or longish-term research to proceed. Okay, and with that, I'm done.